Can you perfectly see the slides?
Yes, we can see them. Thank you.
Because I have some BEMR on, but that's all right. So thank you for giving me the opportunity to describe our collaborative efforts towards high resolution data assimilation in ECMWF IFS. So ECMWF aims to continuously enhance the resolution of the IFS and thereby delivering forecasts with progressively finer details and progressively greater skill. For example, the cycle 48R1 applied an improved resolution of the ensemble forecasts, followed by the most recent cycle 49R1, which applied an improved resolution of the ensemble data assimilation. So effectively, it was scaling the resolution from TCO 639 to TCO 1279, which in terms of the grid point resolution means going from 18 to 9 kilometer resolution. At such resolution, the IFS is now able to resolve the mesoscale extreme weather phenomena and also quantify the probability of their occurrence. However, the goal of the Destination Earth Continuous Extremes Digital Twin is even more ambitious. So the final goal is to provide a prediction framework at kilometer scale resolution, resolving the convective scale phenomena. So before I go further, I would just make a brief overview of the current ECMWF IFS data assimilation, variational data assimilation. So four-dimensional variational data assimilation is used, more precisely the incremental formulation of the 4D var. And the incremental 4D var consists of an outer loop and an inner loop. And in the outer loop, we first compute the so-called nonlinear trajectory, which is high resolution and so has the same resolution as the nonlinear forecast. The nonlinear trajectory is used to compute the departures, which are the differences between the observations and the model equivalent of the observations. So by applying, which we get by applying the observation operator on the model trajectory fields. The actual minimization is then performed in a reduced dimension space at lower spatial resolution. So this is the so-called inner loop. And this is done for several reasons, but mostly due to computational costs and also to reflect the density and accuracy of available observations. In this inner loop, the tangent linear model is used to compute the incremental cost function, and the adjoint model is used to compute the gradient of the cost function, which is used to describe the direction in the phase space in which we descend, and hopefully also converge to obtain the assimilation increment. This assimilation increment is then added to the latest guess, and the latest guess gets updated and then fed back again into the nonlinear trajectory, and then this procedure repeats. So it repeats at a total of 4 times currently, or I mean, we have 4 outer loop iterations in the current LVDA framework. On the top right corner, the ensemble data assimilation is illustrated, and the main aim of the EDA is to provide an uncertainty of the background, so the so-called flow-dependent background error variances. And this is achieved by performing the formally described procedure many times, multiple times, with perturbed observations and also perturbed boundary conditions, and starting from a different background from the previous assimilation. All right, so what do we mean by saying high resolution data assimilation? So first, high resolution data assimilation can be understood as an increase of the resolution of the ensemble data assimilation, and that's what has already been done in the recent IFS cycle upgrade, which I already mentioned. The high resolution data assimilation could also be thought as an increase in the resolution of the nonlinear trajectory. And indeed, in this work, we experimentally scaled the nonlinear trajectory from TCO 1279 to TCO 2559, which means effectively going from 9 kilometer grid point resolution to 4.4 kilometer grid point resolution. High resolution data assimilation could also be understood as a high resolution 4D var minimizations. So high resolution tangent linear model and high resolution adjoint model. And the increasing resolution of the tangent linear model and the adjoint model is applied successively. to correct the background state by the increments representative of increasingly finer scale atmospheric features. So you can see here we have listed several minimizations. Minimization 1 employs tangent linear model and adjoint model at TL255 resolution. Minimization 2 applies it at the TL319 resolution. Minimization 3 at TL399 resolution, and we did rescale it to TCO399 in this work. So essentially, we were keeping the spectral resolution the same, but increased the grid point resolution. While in minimization 4, we scaled the TL511 to TCO511. So these are the resolution changes which we applied and used in the subsequent experiments, which I'm going to describe. So first, let's take a look at the impact of the increasing resolution of the ensemble DA, of the EDA system. And the clear demonstration of the effect of the EDA resolution enhancement is by visually comparing the EDA spread. So here it's shown for the relative vorticity at 400 hectopascal, which approximately 400 hectopascal, model level 90. And on the left, you can see the relative vorticity spread for the 18-kilometer EDA in the previous IFS cycle. And on the right side, you can see the 9-kilometer EDA resolution representative of the current, of the recent 49R1 cycle. So what you can see is there are some notable differences. And the most notable difference is in the equatorial regions. So in the ITCZ, in the tropical storm track regions, for example, in the northern tropical Atlantic and the Western Pacific, as well as in the mid-latitude baroclinic areas. So in the new setup, the background error standard deviations are actually larger in these areas, which means that the background is less certain in these regions, and the observation might rightfully get more of a weight. All right. So we have also developed the infrastructure which allowed us to increase the resolution of the nonlinear trajectory from 9 kilometers to 4.4 kilometers. And increasing the resolution in the analysis and the forecast resulted in clear improvement in forecasting of the extreme events. So we have tried this using many extreme case events, and the results are very clear. Higher resolution trajectory gives us kind of a better representation of these extreme events. And this is, for example, a forecast. So these are two forecasts of total precipitation between the period of 3rd of August and 6th of August over Slovenia, which resulted in extreme flooding. While both the TCO1279 and the TCO2559, they both kind of underestimated the total amount of precipitation, which was around 330 millimeters measured at some stations. You can still see that there are some distinct differences between those two. For example, the TCO1279 kept the precipitation belt closer to the coast in the southwestern part of Slovenia, while the TCO2559 rightfully put the precipitation over the areas where the flooding actually occurred. And I just thought this is a nice example of the added value of the higher resolution trajectory. Now, I'm going to skip this a bit because otherwise I'm going to run out of time, but the large-scale forecast skill scores are mostly mixed. And you can see this by a combination of blue and yellow patches on these plots, which show the differences in the root mean square error normalized by the control root mean square error. So yes, the large-scale skill scores are mostly mixed, but there is some very clear degradation going on in the tropical UTLS region. For example, we can see this by this increased background error standard deviations measured by the radius and winds in the tropics. So between 10 south and 10 north. And this could be attributed to more active convection in high resolution analysis and forecasts, which leads to enhanced precipitation, diabatic condensation, heating, and also to, for example, stronger headley circulation strength. So there is some work to do before we could operationally apply the high resolution nonlinear trajectory. On the other hand, the impact of high resolution Ford-Ival minimization is very positive. So increasing Ford-Ival minimization, so again, the tangent linear model and the adjoint model resolution, improves the representation of smaller scale features which are present in the wind fields and humidity fields. And this consequently allows for a better comparison with the observations. So let me revise it again. The grid point resolution of the last two minimizations was improved from the TL399 to the TCO399 in the second to last minimization, and from the TL511 to TCO511 in the last minimization. And here you can see that the background error standard deviations, so the O minus B statistics, again get significantly improved throughout the troposphere. This is again for the radial sun winds. On the right, you can see it for the radial sun temperatures. I actually just chosen two conventional observations, but the impact is positive for basically every observation system, which is quite convincing. This also shows then in the reduced root mean square error. For example, here I'm showing it for the vector wind at different lead times. So we can still see some positive impact going on in the higher latitudes at 5-day time. So yeah, the impact is generally positive. Now I'm going to skip this because I'm running out of time, but surely we did some exploration of the synergies between high resolution data assimilation and high resolution observations. Maybe I could return back to this in the question section, but for now I'm just going to skip it and go to the extreme case events. And here I choose the Hurricane Otis event, and this is really a magnificent hurricane which hit Acapulco, Mexico, on October 25th as a Category 5 storm. So the minimum central pressure was 923 HPA, and the maximum sustained wind was 270 kilometers per hour. This storm is also very magnificent because the rapid intensification from a tropical storm to a Category 5 hurricane occurred in less than 24 hours. And yeah, needless to say that the storm resulted in more than 50 fatalities. Many people are still missing, and $16 billion of damage. And for example, on the right, you can see the extent of the devastation. The devastation was probably larger than it should be, also because none of the global or regional deterministic models, or even the machine learning models, were able to capture the rapid intensification. So this is considered as one of the largest major forecast busts in the recent history of weather prediction. So here you have several models listed, and the dotted line showing the best track evolution of the tropical cyclone Otis. So you can see that none of the models even predicted a Category 1 storm.
3 minutes. Sorry to interrupt.
Right. Now, the same forecast bust also occurred in the operational IFS and also in the E-Suite IFS, while E-Suite IFS did slightly better, simulating a Category 1 hurricane at least. So these plots are showing the evolution of the maximum wind speed for the forecast initialized from different initialization times. So for example, this one was initialized on the 23rd of October at 00 UTC. This one was initialized on 12th of on 23rd of October, 12 UTC. And the blue line is showing the E-Suite case with the TCO 1279 EDA, while the red line is showing the operational case with the TCO 639 EDA. So you can see there is always a difference. The blue line somehow better aligns with the best track estimate of the tropical cyclone storm. So why did this happen? Let's check. So here I did kind of a cycling experiment, but it's not really cycling. It's just showing how the E-suite is better following the tropical cyclone strength than the operational run. And now let's check why this actually occurred. So let's look at the EDA derived background error standard deviations. This was the largest change between the two experiments. So on the left side, we can see the EDA background error standard deviation for the relative vorticity at the bottom model level for the operational case, so TCO 639, 18 kilometer grid resolution of the EDA. On the right, we can see it for cycle 4901 with the EDA at TCO 1279, which is 9 kilometer grid resolution. And you can see that the EDA relative vorticity spread is larger in the case on the right. So the background information is here thus ascribed to be more uncertain, which in turn could give more weight to the observations in this area, which are then able to further constrain the analysis closer to the truth. And now let's see how this evolves with time when the tropical cyclone is approaching the Mexican coast. So we see it's getting even larger. The difference is getting even larger. So this means that we could, in principle, give more weight to the observations in this area. So what was the reason for the forecast bus? I'll go really quickly here. So the forecast model first failed to capture the early intensification of tropical cyclone Otis. So that's the deficiency of the forecast model. And then when Otis rapidly intensified, the observation departure from the background was already very large. And then this led to several observations being rejected already at the first gas departure check, and they were not fed into the 4DVAR. An example is for the scatterometer below. So you can see all scatterometer observations. These are after thinning, and also some of the observations here close to the tropical center, tropical cyclone core got rejected, which is not shown here in the E-suite because E-suite had larger background error standard deviation as well. So yeah, that's basically what I was showing. Another reason was that there were not many conventional observations over the tropical cyclone area at the time, no buoy measurements of surface pressure in the TC storm track, no direct radio soundings, no aircraft reports, and there was only one reconnaissance flight with drop zones, which were fed into the 24th of October 12Z cycle. And even these observations, as you can see, were mostly discarded. Now, another reason is the inability of the 4DVAR to properly capture the large spatial gradients in the core of the tropical cyclone Otis with the operational resolution linearized models. So we asked ourselves, what about if we increase the resolution of our experimental setup? So let's check whether increasing the resolution of the 4DVAR minimization helps. So this is what we got when we increased the resolution of the 4DVAR minimization. So we have the 4.5 kilometer trajectory with TL511 4DVAR in red, and we have 4.5 kilometer trajectory with TCO511 4DVAR in blue. So yes, it does. Scaling the resolution of 4DVAR minimization helps for small and deep tropical cyclones. This is just one example. This is another example. I'll be really quick. This is my last slide. Sorry for a bit of a lengthening. So we try to use these same initial conditions that I was showing with the 2.8 kilometer forecast model, and here we achieved a result which is almost on par with the true evolution. So this was the final setup: TCO 2559 trajectory, TCO 511 and 399 minimization, and the TCO 3999 forecast. So very expensive setup, but we could approach the actual evolution. And here are the conclusions and outlook. I'll be very quick. I would say that further increasing the resolution of the forecast system and the 4DVAR is very important for better forecasting of high impact mesoscale and convective scale extreme events. And just last point, with the rising sea surface temperatures due to climate change, the frequency of rapid intensification hurricane events is projected to further increase, which underlines the need for high resolution systems. And I hope I did demonstrate this need today. Thank you very much for the attention.
Thank you, Ziga. That's very interesting. I think we can have one question because it's a yes or no answer from Olivia Talleyrand. So is the high resolution model still hydrostatic?
Yes.
Okay, that answers that question. Thank you. I think that ends today's talks then. So I think I pass over to the main organisers.